we're actually going to talk about today is dynamic. Now, what is dynamic programming? The first thing I'm going to tell you, this is actually a way of designing solution. It has nothing to do with software. So the word programming there has nothing to do with software, as you will discover soon, okay? And the word dynamic has nothing to do with any kind of memory allocation technique that you have came across in, say, an operating systems course or an embedded systems course. I'm referring by that to, dynamic versus static. Now, historically, dynamic programming was not invented by computer scientists. It was actually belongs to a branch of mathematics that tries to automate the generation of solutions to problems. And this type of exercise in math used to happen in several actually areas within math. There is one area within math called game theory, which studies mathematical and logical puzzles and tries to develop an optimal solution. This can vary from chess to playing XO to all kind of puzzles you came across since even your childhood. So in game theory, in math, they would come up with formal definitions of solutions to such puzzles and problems and games. And one of the things they did is to automate generation of solutions. Now, they often called the generation of solutions as tabulation. Okay? And dynamic programming is one such technique. Now, there are also other areas of math that we're interested in this, including numerical analysis, which is and numerical optimizations, which is actually overlaps a little bit with computer science because it involves the studying or the investigation and studying and the development of fast ways to solve complex equations. There is a number of ways, for example, to solve differential equations. And if you put a differential equation inside a computer, you'd like to solve it as fast as possible. And if you're looking for, a solution to such a problem, you go to numerical analysis. They will tell you how many ways, and they will tell you the ways they have to actually solve, integration or differentiation or differential equations, fast. Now, so historically, it was developed as a technique to generate solutions, okay? But as you will see, there is a number of features in it that makes it perfect to be executed on a computer. But it's not really a contribution from computer scientists. So there are two aspects. Now, let's talk a little bit about this notion of solutions. Okay? Why am I generating too many solutions? If I ask you to come up with a solution to a problem, the solution is going to be one solution. Okay? Even if the problem is multidimensional, like picking the best gym that is close to you and is good enough, it's going to be one solution, one gym name. It's going to be gym number 5 in my list of gyms. Okay? Because it's the closest to me and it's the best gym in terms of equipment or an optimization among those two dimensions. So it's going to be one specific gym. Why are we talking about solutions? And this is really what makes dynamic programming quite unique in a way of thinking and requires a little bit of imagination when you're solving dynamic programming problem. Okay? Now, usually the solution that we are solving for, that is our aim, the one we are looking for, will exist in one cell, and often it is the last cell. So if you look at this figure of m by n array, the solution is going to be in the last cell to the right, in the bottom right corner of the 2D array. Now what about all the other cells? What will be in there? There will be also solutions, but not the one you're after. These are going to be solutions to smaller versions of the problem you're trying to consider or you're solving. Okay? Now, that would sound at the first moment, if you've never seen dynamic programming before, as extremely retarded, because what I'm saying is, and extremely inefficient, that's why it's retarded. Because it's basically saying, if I have a problem, to find its solution, and if the problem has dimensions, 2 dimensions, one of size m and the other of size n, I'm going to find m by n solutions, or generate m by n solutions to reach to my solution. Let me put some numbers here. Let's say I'm trying to solve a problem that has 2 dimensions, just like the gym problem. And on one dimension you have m entries. So let's set m to be 5. And let's set n to be 6. Okay? So what that means, to generate or to find the solution I'm looking for, I have to solve 5 by 6 problems, smaller problems of the same nature. I will generate 29 smaller solutions before I reach to the 30th, which is my solution. Okay? Let's put it again in terms of the gym problem. Let's say you have 5 gyms in your neighborhood. So in the x-axis, which goes from 0 to n, I will put the distances of those gyms to my home. And on the y-axis, which goes from 0 to m, I will put the stars I put with every gym. 0 star, 1 star, so it's going to be from 0 to 5 as well. So it's from 0 to 5 in terms of the distances to my home, and from 0 to n, which is also 5, so it's from 0 to 5 for the stars that is allocated to every gym, that represents how good a gym is. So I will solve not one problem, I will solve 25 problems. And the 25th solution is the one actually I'm looking for. So again, this should sound a little bit strange. And yes, but there is a trick. The solutions are generated from each other. And this is really what makes dynamic programming quite unique. Because if you don't do that, if you don't generate solutions from each other, excuse me, you're doing something retarded. We are together here doing something that's quite retarded. But it is not retarded, because what actually we're going to do, we are going to reuse old solutions, or use old solutions to generate new solutions. And I will always be doing that. And this is a must for dynamic programming. And even though this might still sound a little bit expensive, actually it will turn out to be, in most cases, more efficient and more optimal as a solution than using divide and conquer or greedy. Okay? And we will see a number of examples that will demonstrate this. So again, what I want you to take from this slide is that we are going to build an array, whether 1D, 2D, or 3D, of solutions. In most of the cases you will see it either 1D or 2D. Like the one you have here, it's 2D. And those solutions are being generated from each other. So I start with some trivial solution, and I use it to generate or find the next more complex solution, and then I use that to find the next more complex solution, and this continues on until I find my final solution, which is the one I'm after. So again, to summarize, the big picture, dynamic programming is all about a table that you fill in with solutions, and those solutions are not all to the same problem. Each solution is a solution to a smaller version of the same problem. Okay? That will become clearer shortly. But they are not different solutions to the same problem. They are different solutions where every solution is a solution to a smaller size of the same problem. The one that you are typically interested in and building this whole table for will generally be towards the end of the table. More common it is the last cell in the table. And a characteristic of the way we are building these solutions is that we will use in the next solution we are trying to generate the solution that we have built before, or the solutions that we have built before. Okay? Okay, so let's start by looking at a trivial example to train ourselves on filling in the table and generating solutions from previous solutions. So here is the problem statement. What is the summation of all the pair products between two values m and n, up to including m by n, where n is always greater than m, and the maximum value for n is 5. As the example in the second bullet shows, what I'm asking about, if I tell you what's the summation of 2 to 5, it's going to be 2 by 3 plus 2 by 4 plus 2 by 5. So it includes 2 by 5. And my condition that I am setting is that the second term in the dotted brackets will always be at a maximum of 5, and it always be greater than the first term. So if I build in a 2D array representing m and n will stop at 5, and since n is always greater than m, so m will stop at 4. You notice in the table there's a number of empty cells because according to the problem statement and the constraints embodied there, I don't have a solutions for these cells. For example, 0 by 0, I don't have a solution because n is equal to m in this case. Same thing for 1 by 1, or 2 by 2, or 3 by 3, and so on. Similarly, I don't have a solution for 3 by 0 because in this case n is going to be less than m. So I will now work on the part or the half of the table that I actually could have a solution for. Now, if you look at 1 by 2, well, the solution is easy, it's 2. If you look at 1 by 3, well, the solution is 1 by 2 plus 1 by 3, which makes it a 5. 1 by 2 is 2 plus 1 by 3 is 3. 2 plus 3 is equal to 5. If you look at 1 by 4, it's a 9, because 1 by 4 plus 1 by 3 plus 1 by 2, which the total is again 9. And this goes on for the rest of the cells. For example, 3 by 5 is 3 by 4 plus 3 by 5. 3 by 4 is 12, 3 by 5 is 15, so 15 and 12 is 27. So if we just plug in all those solutions that we know of according to what we are told of what is the definition of what we're looking for, okay, which is the sum of the pair of products limited by m and n as described, we're not doing DP. Because I'm just filling in every cell with the final answer. And in every case, I start from scratch. Like when I was thinking of 2 by 5, I said, okay, what's 2 by 5? It's 2 by 3 plus 2 by 4 plus 2 by 5. That's 6 plus 8 plus 10, okay? And that makes it 24. I don't want to think like this when I'm doing DP. What I want to do is I want to look at the problem statement, and I could actually generate some solutions to figure out what I'm supposedly to do DP-wise, but then I need to fill in the table by using previous solutions. So by the time I reach to 1 by 5, I'm not supposed to recompute from scratch what is 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5. I need to do something else. I need to use previous solutions. And the assumption here in the 2D array is that we're always filling it left or right, top to bottom. So I start with row 0, then row 1, then row 2, then row 3, in the m dimension. So by the time I reach to 1 by 5, I must have passed through all the first row, and I must have passed through all of generated solution, if I can, to all of what's in the second row, which is row number 1, where m is equal to 1, before seeing 1 by 5. And I need to use those. And this is really what DP is all about. So let's try to think about formulating this. What do I mean by formulation? I mean to come up with the objective function. The function that we're going to use to fill in this table. And that function has to refer to previous cells that we have already generated solutions for. Can we do that? That's the question. The answer is yes. If you look at the cell that is immediately to the left of the cell that you are trying to generate a solution for or fill it with value, you have actually been computing along the way what you need to fill in this new cell. For example, by the time you reach to 1 by 5, you must have already filled in 1 by 2 and 1 by 3 and 1 by 4 accumulating solutions there. So 1 by 5 is 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5. Now, if you look at the cell of 1 by 4, which is 9, that's exactly the sum of the previous products. What you just need is to add to it the new term, which is 1 by 5. So instead of thinking 1 by 5 is 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5, I'm going to think of it like this, or formulate it, the objective function like this. It's going to be the left cell, which is the 9, plus the new term, 1 by 5, and that will give me the 14. Now if we do this, and if you can do this, you're on the correct track. You are actually starting to do DP. And this is going to be my objective function. S of I, comma j, or S sub I, comma j, I'm referring to I and j here, I being on the m dimension and j being on the n dimension. I would like to fill in the solution for any one of those cells that I can fill a solution for. It's going to be S sub I, comma j minus 1. So changing the I will take you to the next row. Changing the j by decrementing it by 1 will take you to the previous column. Since I didn't change the I, I'm still at the same row. So j minus 1 is going to be the column just before me, or the cell to the left of me. So it's going to be the solution to I. The solution to the previous problem, which is S of I, comma j sub minus 1 plus I by j, multiplying the indices of the row and column I'm currently at. So basically it's going to be 9 plus 1 by 5. Now, before seeing further examples, let's talk a little bit formally about when to use DP. So given a problem, what you need to check for are two things. That there is what is called an optimal substructure you can work with, which you devise, you come up with, but it has to be possible to come up with an optimal substructure. And we will see what does that mean. And that in the problem, due to its nature, there are overlapping subproblems within the same problem. And again, we will see what does that mean. In order to develop an efficient DP solution to any problem, you have to look for these two things, or you have to come up with these two things. And they really are steps on the way to the solution, in the sense that while you're actually devising or coming up with the optimal substructure, you will be creating the array that we have seen before. And while you're actually figuring out the overlapping subproblems, you will be building insight into the nature of the solution, and that will enable you to write the objective function. So let's see each one of those. The first property is what's called the optimal substructure. This is also called in textbooks the principal of optimality, or generally optimality. Let me read this and then I will describe it. It says a problem has optimal substructure if an optimal solution can be constructed efficiently from optimal solutions of its subproblems. More simply, we can solve large problems if we are given or we have found solutions to smaller problems of the exact same type. This is actually what enabled us in the previous example to fill in a cell from previous cells or from the left adjacent cell. To be able to reuse solutions in a DP table or in the DP array, to be able to reuse previous solutions and reach finally to an optimal solution, that means every solution we are using from before, every previous solution we are currently using to create a new solution, that previous solution must be optimal. So I am claiming that now I am generating a new optimal solution for a problem of a specific size because I know that the previous solution I am going to use to create this current solution, that previous solution was optimal for the problem size it was solving. So I generate, if you'd like to think of it as a sequence of actions, I start by a trivial problem and I will solve it to find a good trivial solution that is optimal. There is no better one. And then I will enlarge my problem size, trying to find the optimal solution for this new size by using the previous optimal solution. That's exactly what we referred to several times as using previous solutions. But now I'm adding the condition of optimality in order to get a final optimal solution. Now, if you are able to do that, then your final solution is going to be optimal. But to be able to do that, what you need to actually to structure the problem so you can actually work always with optimal solutions or come up always with optimal solutions. So you have to structure it so that at every step the solution you're currently generating is optimal by using previous optimal solutions. Now, this might sound like either very easy or very tricky to you. It will be very easy if you understand just the idea that, okay, I'm having one optimal solution to a problem of size n, and if I enlarge the n a little bit, I'm going to use that optimal solution to generate a new optimal solution. And you're perfectly okay in your understanding. There's nothing wrong about what I just described. But it will feel very hard for you, or you will think of this as being a very hard idea or a very difficult concept to digest if you just keep thinking of this notion of the substructure. And yeah, there's a little bit of trick there. It is not easy to actually always come up with the optimal substructure. Okay? If you find it, then you're way ahead. If the problem yields itself to easily find or locate the substructure upon which you will continuously build optimal solutions, then you're done with this step. Okay? But sometimes it's a little bit hard. You'll have to think about it. And again, this is a matter of training here. If you keep solving DP problems, you will immediately be able, you will gradually be able to pick up the substructure that you need to be working with. Okay? Now the substructure itself will come as a concept from the problem statement. Okay? And the thing is, every problem or every class of problems will have a similar substructure. So the more problems you solve, ultimately you will see all the substructures you could work with. Okay? There is some ambiguity, of course, in what I'm describing because you really didn't see a substructure yet. But the idea, I hope, is clear that we need it, and we will continuously use the same substructure. We'll just be enlarging it. And this substructure, if we picked it correctly, every time we generate a solution, it's going to be the optimal one. And since we can continuously use these optimal ones one after the other, as we keep filling in the table with solutions, then our final solution is going to be optimal. There is no way there could be a more optimal solution, because you were always picking the best possible solution. Okay? I know that this is a little bit kind of high level in description, but just wait with me until we see more examples. Now, the next property, which is related but is not the same issue we're talking about here, that a property of finding an optimal DP solution is that the problem itself have subproblems that are overlapping. Okay? So the idea is that, as this bullet says, the same subproblem appears over and over again. Let me give you an example. When we talked about the summation, when I say, what's the summation of 2, 5? It's going to be 2 by 3 plus 2 by 4 plus 2 by 5. Okay? What is the summation of 2 by 4? Or 2, 4? It's going to be 2 multiplied by 3 plus 2 multiplied by 4. Okay? Now here are two different problems. The solution to summation of 2, 5 and the summation of 2, 4. In both, you are solving 2 by 3. So that's what's called a subproblem that keeps appearing over and over again. And this is very important to be able to reuse previous solutions. Okay? So the property that you need to be looking at in the problem statement, if you have subproblems that keeps appearing, because this means you can reuse their solution later on. Once the first time they appear, you will solve them. The second time they appear, and the third time they appear, and any other time they appear in, you will use the solution that you've devised the first time. Okay? Now, this actually will give you in the objective function a recursive formulation. If you look at any objective function in the DP literature, there is always a recursive formulation. Okay? We are solving a problem in terms of some other problem that is of the same nature but of a smaller size. And that will give you this recursive definition that you will see over and over. Okay? Now, have you seen anything that's close to this before in your computer science education? Yes, of course, Fibonacci numbers. Okay? Let's work out the following Fibonacci code that appears on the right side. You know, the Fibonacci of 0 and 1 is Fibonacci of 0 is 0, Fibonacci of 1 is 1, and then the Fibonacci of any number is the sum of the Fibonacci of the previous two numbers. So this is what appears in the code on the right. If n is less than or equal to 1, I'm just going to say return 1, else I will return Fibonacci of n minus 1 plus the Fibonacci of n minus 2. Okay? Now, let's expand the Fibonacci of n. The one we have in front of us in the code. It's the Fibonacci of n minus 1 plus the Fibonacci of n minus 2. Let's expand Fibonacci of n minus 1. It's going to be Fibonacci of n minus 2 plus Fibonacci of n minus 3. Now, notice we have Fibonacci of n minus 2 at the bottom left of the tree, and we also have it at the second level on the right, as the right child of Fibonacci of n. And the same thing, Fibonacci of n minus 3 is repeated. So if you're actually building this tree top to bottom, left to right, you should, if you're doing it DP-wise correctly, you should calculate Fibonacci of n minus 2 once, and when it appears again later on, you will reuse your previous solution. So you don't have to compute it several times. So Fibonacci is actually an example of a problem that has subproblems that keeps repeating. Okay? Now, if you think of Fibonacci of n minus 5, how many times this will repeat? It will repeat several times, because as you keep expanding this tree until you hit the leaf level, where you're working with Fibonacci of 1, and every one of those subtrees that I have shown here, you will see Fibonacci of n minus 5. Okay? So the notion that you save computations by calculating a value and reusing it in the Fibonacci example becomes very clear. It's going to be very profitable to you. Okay? In fact, later on we will see a comparison of the non-DP version of solving Fibonacci and the DP version of solving Fibonacci, and the difference will be quite significant, as you will discover. Okay? Now, here is an example with an actual number, Fibonacci of 5. Look how many times we have repeating subproblems. If I want to answer Fibonacci of 5, I have to solve Fibonacci of 4 and Fibonacci of 3. Inside Fibonacci of 3, Fibonacci of 4, I have to solve Fibonacci of 3, which I'm going to ask about it later on. That's Fibonacci of 3, and I have to ask to solve in the 3 highlighted in the leftmost part of the sub-tree highlighted in the leftmost part of the whole tree. I will solve Fibonacci of 2, and look how many times I need to answer Fibonacci of 2. I will need to answer that again 2 more times later on. Okay? And the same thing for Fibonacci of 1 and Fibonacci of 0. They're being, I'm being, faced with this problem over and over again, which is, Fibonacci of 1 and Fibonacci of 0. Okay? Now, and this is why I've written at the bottom, it says this is why overlapping subproblems is a precondition to a DP solution, because this is what enables us to use previous solutions in the array, in the DP array. Okay, and this is just a highlight of what I'm just describing. Now, how would we solve this DP-wise? Remember, DP means array of solutions. In the case of Fibonacci, actually, because the problem is quite simple, I really have one dimension here, which is the Fibonacci value I am trying to find. This is not a multi-dimensional problem. This is a single dimension. I just have to figure out Fibonacci. Okay, there's nothing else to consider. So the solution to a Fibonacci, or the DP solution to a Fibonacci exercise, is nothing but a single dimension array. I fill in the first value with 0 because the Fibonacci of 0 is 0, and then I fill in Fibonacci of 1 is 1. Okay, and then starting from the cell whose index is 2. Okay, I will add up the previous 2 entries. That's why you see the 1 is there. And then this continues on. After the 1, I have a 2, and after the 2, I have a cell with the value 3, and this goes on all the way till the value I'm looking for, which is the Fibonacci of n. So notice that this array, I will pass on it one time from beginning to end, so it is, at worst, it is actually O of n, okay? It's not at worst, it's always O of n. Best case and worst case is O of n, and it takes O of n space. Now the previous code that we were looking at for calculating Fibonacci, I want you, as an exercise to go and Google it and see what is the asymptotic order of it, okay? So you will find like a huge difference in the asymptotic order. This, as I'm mentioning, it's O of n. So if you haven't already Googled that, if you haven't stopped the video and tried to Google that, what you're looking at here is the code we've seen before, and this will run in 2 to the n by 2. I will not show you now why it's 2 to the n by 2, but you can safely assume it's 2 to the n, which is a ridiculous number, by the way, for any Fibonacci value, especially if the value crosses 10. Now, n crosses 10. Now, on the right side, we have the DP version, which is O of n. Quite a drastic enhancement in the performance. There is also something I would like to note here. If you look at the Fibonacci code on the right, this is the DP solution, and often DP code is close to being trivial most of the time, if not all the time. Why? Because I have an array and I'm going to fill it with solutions. So how do you fill an array with solutions? It's going to be a for loop. Even if it's a 2D array or a 3D array, it's going to be a for loop, nested for loops. Okay? So this is one thing that's actually quite interesting in terms of performance, that the code for DP, the code to solve any DP problem, since it's just a bunch of for loops and if statements, its execution is going to be super fast. okay? We don't have generally recursion formulations or recursive code for solving DP, although it is possible, but in most cases you don't need that, okay? It's just going to be a simple for loop. And that's really interesting because CPUs are optimized for running, simple for loops like the one in front of us, okay? Especially if the calculations in the body of the for loop is a mathematical calculation. And you only have a handful of them, 1 or 2 instructions, and that's in most of the cases. In the case of DP, what we will be doing, okay, it's just going to be some simple mathematical addition or subtraction or multiplication. There is nothing really more complex than that, and CPUs are really super fast in executing such a piece of code, compared obviously to the one at the left where you start using recursion. In fact, you have here what's called two-way recursion. So you're going to use more space on the stack, and you're going to be sending information on the bus back and forth between the memory and the CPU. So this is, in terms of the performance, it's much slower, orders of magnitude slower than the code on the right, and execution-wise is also going to be a challenge for the CPU. So let's look at a more sophisticated problem that will be solved optimally by DP. This is the 0-1 knapsack problem. I have talked about this problem when I explained the greedy technique, and I told you that the greedy method would come up with an optimal solution if you are working with the fractional knapsack problem, where you take a portion of an item. But what if you cannot take fractions? What if you either can take an item or leave it? You cannot cut pieces from it and include it in the bag. In this case, this is going to be the 0-1 knapsack, and this cannot be solved optimally by greedy, but it will be solved by DP. Now again, it's the same problem we've looked at before. I have a bag of a maximum weight, and I have a number of items. Each one has a weight and a value. My goal is to fill in as much of the bag as possible, having taken the most valuable items I can possibly pack into the bag. So I'm really here optimizing along 2 dimensions, the weight and the value. I would like to maximize the value, but I would like my weight also not cross a certain value, which is the 20 kilograms, what is possible to go in the bag. So going to think about a DP, my step number 1, I would like to identify what we have described before as the optimal substructure. So this is really your first time to see the notion of a substructure spelled out. Okay? Now, this is how I'm going to think about it. It will sound a little bit complicated at the beginning, but then it's really common sense if you'd like to think about it in a little bit deeper way. So don't be taken away by the complexity of the title, optimal substructure. What am I after with this notion of a substructure? I am after continuously finding optimal solutions, starting from not the problem I am trying to solve, but starting from a trivial instance of the problem. Okay? So what would trivialize my instance? If you go back and look at the previous slide, I had a bag of 20 kilos. Okay? And I had, say, 6 items. What is a trivial version of this? Perhaps the bag weight will decrease. Perhaps the number of items will decrease. In fact, if both of them decrease, then I'm supposed to be able to solve the problem easily or easier because I'm working with less. So instead of being worried about which of the 6 items will go in a bag of 20 kilos, if I ask you, if you have a bag of 10 kilos and 3 items, will you be able to figure out the optimal solution compared to 20 kilos and 6 items? And the answer should be yes. In fact, let's actually even trivialize it a little bit more. If the bag has a maximum weight of 5 kilos and you have 2 items, wouldn't that be easier? And the answer again is yes, because the problem is getting simpler, because the values are getting smaller. In fact, the most trivial of all is if I have a bag that has 0 kilos allowed and I have 0 items. So pretty much I'm not going to do anything. I'm going to say I will make a profit of $0 because there is nothing I could put in the bag and the bag cannot hold anything. Okay? This is thinking about the optimality thing. What I'm doing now is I'm thinking about optimality. To reach to an optimal solution for 20 kilos and 6 items, I have to consider 19 kilos and 6 items, and I also perhaps need to consider 19 kilos and 5 items, and 18 kilos and 4 items, and 10 kilos and 3 items, and 5 kilos and 2 items, and 1 kilo and 1 item, and 0 kilos and 0 items, okay? If I can generate optimal solutions to all of these variations from 0 and 0, 0 kilos and 0 items, all the way till 20 kilos and 6 items, I've done it DP way. Okay? This is what I try to spell out here in the paragraph. It says consider problems of smaller weight, i.e. to find optimal configuration for items in bag of maximum weight 5 kilos, solve for maximum bag of 4 kilos, and for that solve for maximum bag of 3 kilos. Okay? This is what the substructure is about. This is what optimality is about. I'm not going to jump and find the optimal solution I'm looking for. What I'm going to do is I'm going to start from a trivial case and find the optimal solution for it, and then move on to a slightly bigger case, find an optimal solution for it, and then use that in the next optimal solution I'm going to be looking for when I enlarge the problem by a little bit more. Okay? Now, let's go to this specific problem. What are the dimensions? And this is really the part that some students will find difficulty digesting, because the dimensions will change from one problem statement to another. What am I actually after? I'm after filling in the weight of 20 kilos. Okay, but I'm also after which item to pick. So I will put the weight on one dimension, and I will put the items one by one on the second dimension. So if you look at the items side, which is the y-axis, it goes 0, which means there's nothing to include. And then 1, which means I'm looking now at the first item, whichever that one is. And then 2, which means I am looking at the second item in addition to the first item. So I am now solving the problem where I only have 2 items. And when I'm at the third row where it says 3, then I'm looking at the problem where I have 3 items. So the tricky part about 1-0 knapsack is to figure out that the dimensions are the weight, the possible weights. If my maximum is 20, I will go through all possible weights from 0 to 20, finding the optimal solution for every weight. And then the second dimension are the items themselves. Not the prices of the items themselves. And I will go through the items, adding one item at a time to my input. So I will imagine I only have 2, and I solve for that, for all weights. And then I have 3 of them, and solve using those 3 for all weights, finding optimal solution in every cell. Now, step number 2, which is the recursive formulation or the overlapping subproblems. Okay? How can I go about it? You need some intuition here. Let's forget about DP. Let's say I give you 3 items, and I tell you I would like you to eyeball it. which means just to work it out yourself using your intelligence, to pick from the three the best combination that will fit in a bag. So let's say you go about and about it this way. You pick the first one and put it in the bag. Then you suddenly find that the bag is full. You look at the weight of that first one in the bag, and it's equivalent to the weight of the bag. So if the bag is 10 kilos, that item is 10 kilos. And then you look at its value and you find it's $1. Then you go and look at the other two items. And you see that the two of them make 10 kilos, but their total sum is like $50. So you have a bag of 10 kilos, you've put an item that is worth $1, you put it in the bag, and now the bag is full. And you look back and you say, oh, okay, well, I picked the first one, I put it in the bag, but it's equivalent, it's going to give me $1. And I have now in front of me the second and third item together, they're worth $50. And they together can fit in the bag. So I have just made a bad decision by putting the first one in the bag. So you take it out from the bag and put instead of it the other two. Now the bag content is full in terms of weight, and the value is $50, which is much better than $1. Okay? Now, remember, what are we after when we're trying to define the objective function or come up with the recursive formulation? What we are after is we would like to identify the repeating subproblems so that when we code or when we build the objective function, we refer to the previously calculated optimal solutions. Okay? So, what am I going to refer to? I'm going to refer to the previous solution that I have built for a specific weight, but I need to also consider my current weight. So my recursive formulation should allow for me to do the action I was just describing, which is to take an item from the bag and put something else in front of it. Instead of it. And that's exactly how we do it intelligently, without DP. Okay? I will try to put certain items in the bag, I will look at their value, and then I will look at what's outside later on. And if I see that what's outside the bag is more valuable than what's inside the bag, I will take what's in the bag and put something else instead of it. So, and I will continuously be doing that. I know this is a little bit hard to digest when you first think of it, but this is really the essence now of DP. So try to concentrate with me. So I try to model it here for you again, just to get the idea before I show you the formulation. So you know your maximum weight, and you have these items, and the size of the items reflect their weight. So the smallest item is worth $1, the second smallest is worth $2, the one in the middle is worth $7, and the red one is worth $8, and they are in increasing size. So remember, DP, I don't find a solution to the whole problem. So the whole problem here is you're giving this empty bag and you're giving 4 items. So there will be an optimal solution to the bag empty and the 4 items, but I'm not going to solve that. I'm going to solve a smaller subset. So I will solve the subset first. The most trivial one is I only have 1 item. So as if, my input now only has 1 item, which is the $1 bag. So I put this one in the bag, because that's the only thing I know now that I have. I haven't seen the other ones, the 2 and the 7 and the 8. So what I do is, every time I come across an item, I will put it in the bag, and I will continue on, as long as the scale didn't alert me that I have reached the maximum weight. If I reach the maximum weight, I will remove the item that I just added. This is the essence of what we will be trying to do in DP. So I add the $2. When I add the $2 item, I am told by the scale that, okay, the maximum weight has been reached. Okay? So if I try to put the $7 plus the $1, I will also be told the maximum weight has been reached. So I will remove away the $1 and put the $7. Why? Because 7 is greater than 1 in terms of dollar values. Again, this is what we will do it intelligently. And then I try to add the $8, but again I will be told the maximum weight has been reached. So I take away the $8. 1, and I keep the $7. Along the way, I should also have tried to put the $8 alone, but the scale told me that the maximum weight has been reached, so I will keep the $7 one. Okay, so the $7 is the only one that will go in the bag without the scale alerting me that the weight has been exceeded. The $8 will not go into the bag, okay, and the 1 plus $7 will not go into the bag because the weight will be exceeded. Okay, so the $7 is the optimal solution. And obviously, you know, if the $1 one plus the $7 one will not go into the bag because there's no space or there is no weight, then for sure the $2 one will not go into the bag as well. Okay, because the 7 is already there. So this kind of behavior of putting things and then taking them out is very critical to understanding the solution. Okay? Now, and this is again what I was just describing that I will try after adding the 7, the 1, and the 2. And again, I cross the maximum weight, so I will take them out, and the 7 is my optimal solution. So let's work out a specific instance. So the other cells are going to be filled by the objective function. This is what I'm going to do. I'm going to solve this table one row at a time. This is how we do it in DP. One row at a time, from top to bottom. Since I have laid down the items on the y-axis, and I'm solving a row at a time, I got my first row filled in with zeros. My second row, I have item number 1. So I'm going to think of the following. This is again the substructure we were referring to. As if all what I have is just this one item. I'm not going to look at the other ones. I'm not going to assume even they are there. It's as if all my world and as a problem statement consists of only one item. I would like to find the optimal solution using only one item. But I will solve how many problems? I will solve 5 problems. 1 item and 1 kilo, 1 item and 2 kilos bag, 1 item and 3 kilos bag, 1 item and 4 kilos bag, and 1 item and 5 kilos bag. Each one of those cells is an optimal solution for a smaller version of what I'm looking for. I'm looking for 5 kilos and 4 items, but now I'm only going to process 1 item, and I will solve for all these bag sizes from 1 to 5 kilos. Okay? So, what I should be checking is, now, since I only have 1 item, can the item go in the bag or not? Now, what's the condition here? The condition is that, or the constraint, that the weight should be below or equal to the maximum weight. So in the case of my item 1, the weight is 2 kilos and the value is 3. Actually, when I told you in the previous slide, I kind of reversed them. So just keep in mind that the weight is listed first, not second. So the weight is 2 kilos and the value is $3. So if I'm having a bag of 1 kilo, obviously this will not fit. But if I have a bag of 2 kilos or more, this will fit in that bag. Okay? My weight now, if it's 1 kilo, this cannot fit. Now, the weight minus weight of the item is -1. This cannot fit. Okay? So I'm going to write the code as follows. If the weight of the item is less than or equal to the maximum weight I can put in the bag, then I need to check, can I put it or should I ignore it? Again, this if statement is saying if the weight of the item is less than the weight of the bag, then consider the item, otherwise just ignore it. Okay? But this is what we're going to do. This is the tricky part. I will need to decide, should I include it or not? But here the inclusion has a little bit more thoughtful approach. And instead of saying just append it to what exists in the bag, since I'm trying to always generate optimal solutions, I will figure out if I can remove something from the bag and put it instead, and the total value will be more. This is why you see this nested if statement. It says if the value of the item I plus what's in the bag without the equivalent of the weight of I is greater than what's in the bag without I, then add I. Let me read it again. This is really the crux of the whole thing. It says if V of I, the value of the item I, which in our case is $3, plus what is B I minus 1 W minus W of I? It's what's inside the bag. Now, B is referring to the two-dimensional array at the top. I minus 1 means go to the previous row. Go to the previous row means without the current item. Comma, which column? The weight that I'm currently considering without the current weight, W minus W of I. I will repeat over, I will show you a trace for all the cells so you understand completely what this means. So I am excluding the current item and excluding the weight of the current item. I will go and look in the array in the cell without this item, which I minus 1, without the weight of the current item, or the equivalent weight of the current item, which is W minus I. And if I figure out that the value of this B plus the value of the current item, the number that will be I minus 1, W minus W I will resolve, plus the value of the current item, is greater than what? What is B I minus 1 W? I minus 1 means without the current item, because I'm going to go up one row, but the same weight. I'm keeping the same W. Okay? In other words, there is something in the bag I can remove that is equivalent to the weight of the item. And when I remove that thing and add the current item, the total value in the bag is going to be bigger. If that's the case, then the line nested inside this if statement says BIW equal to V of I, the value of I, plus whatever in the bag without the equivalent weight, which means, let me try to put it to you. Again, we will see this in traced throughout all the 2D array we're looking at. But let me try to conceptualize this again for you. Let's say I'm having an item that is 2 kilos, which is the one I'm holding now. This is item number 1. I'm not just going to go and add the 2 kilos to the bag because the weight allows. No. What I'm going to do is I'm going to look in the bag if I can remove another 2 kilos from the bag and put the new 2 kilos I'm holding for the item I'm now considering, and the sum is going to be more. Okay, so let's see what's currently in the bag is 10 kilos, and I'm trying to add 2, and the bag allows. But if I just add this new 2 to become 12 kilos, I'm not generating an optimal solution necessarily. What I'm going to do is, to make sure that I'm generating an optimal solution, I will look among those 10 kilos, can I remove 2 and add my new 2, and the sum is more in terms of value. So let's say the current 10 kilos had a value of $50, and the new item has a value of $10. What I'm going to look at inside the bag is, can I remove out of those 10 kilos 2 kilos? And when I find actually that I can remove 2 kilos, I'm going to ask the question, are these 2 kilos I am removing worth less than the 2 kilos I'm adding? If it is the case, I will add the 2 kilos. So let's say I identify 2 kilos that are worth $1, and my new 2 kilos are worth $10. So I'm going to remove the 2 kilos that is worth $1 and add the 2 kilos that is worth $10. This is the only way I can guarantee that I will always be producing optimal solutions, because there is nothing better. There is no way there could be another optimal solution that exists, and I'm not picking it, because I'm always replacing less valuable items with more valuable equivalent ones, equivalent in weight but greater in price or value. And this is what this nested if statement that says, if V of I plus I minus 1, which means without the current item, W minus WI without the current weight, okay, or the total weight minus the current weight, the 2 kilos I'm referring to, if it is greater than without the current item with the current weight, which means, let's say in our example again, the current weight was 50, and now when I add it, I removed one that is worth $1, so it's going to be 49 plus 10, so it's going to be 59 instead of 50. Okay? And then I add it. So let's try to apply this on item 1 for weight 1. Now, for weight 1, the value is 3. But the problem is WI, is less than or equal W. Is it true? No, it is not. I'm asking, is it the case? The weight of I is 2. So WI is 2. And the weight is 1. So I cannot put it in. Okay? So what I'm going to do is, and this is what you see here, I am going at the last statement that is highlighted in blue. If I cannot put it in, I'm saying BI of W, the one I'm trying to fill in, is equal to BI minus 1W, which means I minus 1 means go to the previous row, look up the solution for the W weight. So it is really where the item index was 0 and the weight is 1. And the solution we have put already in the initial values, kind of trivial values, filling in from the code in the previous, okay? Because the optimal solution is going to be the solution without the current item for the same bag, okay? Now, when we look at, again, we're at row number 1, for item number 1. When we look at the solution for the weight equal to 2 kilos, what am I going to get? Well, the first if statement is going to succeed. The weight of I is 2 kilos. The allowed weight in the bag is 2 kilos. So weight of I, 2 kilos is less than or equal to 2 kilos. We will go inside the if statement. And now the question is, okay, since I have space in the bag, should I add this item or not? My criteria is the second nested if statement that says if V of I plus. Now, again, what I'm going to do is, the value is 3 plus B of I minus 1, W minus WI. which means I minus 1, go one row up. W minus Wi, it means W will resolve to 2 minus Wi will resolve to 2, so it's 2 minus 2, so I'm going to go to 0, 0. The I minus 1 will resolve to 0, W minus Wi will resolve to 0, so I'm going to go B of 0, 0. And the benefit there was 0. So it's going to be V of I 3 plus 0, is it greater than I minus 1, which is again 0 and W2. So it's 3 item. Okay? So again, the first if statement will succeed because the item weight is 2 kilos and the bag now is 3 kilos. So I will go inside and then now I will check. Is the value of I, which is $3, plus BI minus 1, which means go up one row, W minus WI, 3 kilos minus 2 kilos. So that's going to be 1 kilo. Okay? Is the new item plus the profit from what is inside the bag without the weight, the equivalent weight of the item I am processing, which is item number 1, is the benefit going to be more or less? It's going to be more, because if you look at the arrow, the blue arrow, it's referring to 0 items and 1 kilo. The benefit was 0, so it's 2. Now 4 kilos, again I'm comparing 3 kilos with $3. Everything goes for the last one. Okay, now let's go along. Now when we start processing the second item, that doesn't mean I am processing it separately apart from the first item. I am assuming that now I have the first already in there, and I am now grabbing the second one and trying to figure out, should I add it to the first or remove the first and add the second, or just keep the first and not to add the second. Okay, so I have here 3 cases. Either I add the second to the first is either already in the bag or not. If it's in the bag, I have an option either to add the second to the first or remove the first and add the second. Okay, or keep the first and not add the second. So the items labels 1, 2, 3, 4, it doesn't mean I am picking one at a time and ignoring what I have seen before. I am accumulating on what I have seen before. Okay? Now, so we're going to go through the same logic. Item number 2, its value is $4 and its weight is 3 kilos. Okay? Now, so when I'm solving for item 2, which means item 1 and 2 together now, when I'm solving for that and the bag size is 1 kilo, I can neither put item 1 or put item 2. I have already solved for item 1, so I'm just going to talk about item 2. I cannot put item 2, so I'm just going to get the solution for the bag with 1 kilo without item 2, which is going to be in the row above it, which, as you notice, we obtained it from the row above it in the previous run for item 1, for the bag of size 2 kilos. Okay? Now, if the bag size is 2 kilos, and since this item 2 weight is 3 kilos, I'm going to accept the solution without this item, which is going to be the solution for item. Now we're going to move on to the solution for a bag of 3 kilos. Now 3 kilos is interesting because the item weight is 3 kilos. And the bag size now is 3 kilos. So let's actually talk about this in plain English. If I give you a bag of 3 kilos and I give you 2 items, one of them will give you a benefit of $3 and the other one will give you a benefit of $4. Which one would you pick if both of them fit in the bag? You will pick the item that has a value of $4. This is the situation we are at here. Item 2 value is $4. The bag is 3 kilos. The item weight is 3 kilos, so the item can fit in the bag. But notice that since I already processed item 1, I have put item 1 in the bag of 3 kilos because item 1, weight was 2 kilos, so it can fit in a bag of 3 kilos. So I've already put it there, but item 1 value is $3, and I now have a better item that has value of $4. So what I do is, I'm going to not, what I'm looking for basically is a way to remove item 1 and put item 2, because that's really the optimal solution. So what I'm going to do is, I will compare the value of what's in the bag without the current weight of the item, which is 3 kilos, or the weight of the current item, and see if the value will increase. Why am I saying I will look into the bag again without the weight of the current item? Because I'm trying basically to find out if I can remove something, or remove a part of what's in the bag, or an item that is in the bag, and increase the total value in the same time. And this will again take us to the same code that we looked at before. It's going to be bi minus 1, which means ignore the current item for now, this new one. Okay, go up 1 row and tell me what was the benefit, what was the gain for W, which is 3, minus the current weight of the item, which is 3, minus the weight of the current item, which is 3. So tell me the benefit of 1B10. So tell me the benefit when you had one item and the weight was 0, which will take us to the cell that the blue arrow is coming from. So tell me the gain there. Now, this gain, I'm going to add to it V of I, which is the $4. And then I will compare this $4, is it greater than BI minus 1 W? I minus 1 means go up 1 row. W means the same weight. So it's like saying if 4 greater than 3, yes, 4 is greater than 3. Okay? If it's the case, then I'm going to add this item to the content of the bag without the equivalent weight of this item. And that. Next, we will proceed to the next problem, the bigger problem, which is a bag of 4 kilos, and we're still having the second item. We will go through the same logic, and we will find that the second item is better than the first item, so we'll say that our gain is $4 instead of $3. The next bag size we're going to look at is the bag size of 5 kilos with the 2 items. Now this is interesting case because the bag weight is 5 kilos and the addition of the weights of the first 2 items are 5 kilos. So we were always looking into replacing an item by another if the value is more. But what we will run into here is a case where we can put the 2 items and the total value of both will be more than any one of them alone. And this is what the code supports. Let's see how this will work. Now I'm currently considering, again, I'm at row 2, or the second item. The weight of the item is less than the weight of the bag, so the first if statement will be satisfied. I will go in and I will do the following check. A V of I, which is $4 plus what exists in the bag without the current item, so it's I minus 1, comma, W minus WI, which means 5 minus 3, that's 2. So I will actually be looking at the cell that has the blue arrow coming from. I will compare 4 plus 3, which is 7, greater than BI minus 1, which is without the current item, with the weight, which is the 3 above it, the 3 above the cell I'm trying to fill. So 7 greater than 3, yes. I will go and add the item to what currently exists in the bag without its weight. Without its weight, it's 3 kilos. Without its weight, it's 2 kilos. It's 5 minus 3, it's 2 kilos. So I'm going to add the second item in addition to the first item. And that's why you see now that I'm calculating my value as 7. And again, if you think of it in plain English, I have a bag that's 5 kilos and I have 2 items. One is 2, another one is 3. And I'm looking for an optimal solution. So obviously I should take both of them. And that's what this formulation is allowing us to do. We'll move on to the third item. We have been generating solutions to all bag sizes from 1 to 5, including item 1 alone, and then including item 1 and item 2. Now we will include with us as well item 3. So I will solve for with item 3 and a bag of size 1 kilo. Now obviously this is not very helpful because item 3 weight is 4 kilos and I only have a bag of 1 kilo. So I'm going to borrow the solution that is optimal for that bag size without my current item since I cannot put it in. Now I will also do the same for the next cell and the next cell. I'm just going to put in whatever optimal solutions I have found before, because this item weight I cannot simply add, because again the item weight is 4 kilos and I have been considering bags of sizes 1, 2 and 3. So whatever I have found before, and this is the essence of DP, that we use what we have found before. Whatever we have found before, ignoring the current item, is an optimal solution for that bag size that we're looking at. Now when we go to bag size of 4 kilos, and since this guy weight is 4 kilos, the question becomes, should I add it or should I not add it? Now notice that the value of this item is 5. Without the weight of the current item, I mean by that excluded from the bag, I'm comparing 5 and 0, so obviously I'm going to add it. Okay? It's as if for the case of the bag size of 4 kilos, I started fresh from an empty bag and added it. Common sense, English-wise or English thinking or common sense thinking says, if I have a bag of 4 kilos and I have 3 items, one is worth $3, other was worth $4, and the third one is worth $5, which one should I pick? So to consider that, I have to go to the case where I haven't added anything. So I will subtract whatever item weight I'm trying to add from the current weight of the bag. It will give me the bag without this item weight, and I will check its value and I will compare it against the value of the current item. 5 and 0, 5 is more, so I will add the item. Okay? So the optimal solution, if you have those 3 items we have been discussing and your bag size is 4, is to pick the third item, which is 5 kilos. Now we go to the next one, and we go to the situation of the 5 kilos bag. Now in the 5 kilos bag, I will be comparing between basically adding my current item, which is item 3, and the previous optimal solution, which is 7. And obviously 7 is more, so I will put the 7 in. Continue on to the next row where I start considering item number 4. Okay? Item number 4, weight is 5 kilos. So it will not fit in any bag except a bag of size 5 kilos. So I will get from the above row the optimal solutions that I have found. I am just going to plug them as is, according to the statement that is highlighted in blue at the bottom of the screen. Now, when I go to the last cell, the options are going to be, should I include item number 4, whose value is $6, or should I keep the previously found optimal solution, which is $7? Since 7 is more, I will keep my previously found optimal solution. Okay? By this, I'm done with filling in the table, and I have found all optimal solutions for all configurations or all variations of the problem of smaller sizes than the one I'm trying to solve. What I'm trying to solve is 5 kilos and 4 items. I have solved for all kilo variations from 0, and I've introduced one item at a time, and I've considered all combinations, picking every time the optimal one. So the best thing I could make is actually $7. Notice that by looking at the $7, I can figure out who are these items. So what we would typically do, we would keep with us alongside this 2D array another 2D array of ones and zeros, of binary values. Whenever we pick a new item, we put a 1. And whenever we keep the exact value, keep the value that we worked with before, we put a 0. You will see this additional 2D array in the tutorial. This 2D array we're looking at is the one we're after. We would like to find the maximum value that we are can gain from a bag of 5 kilos, which is $7. But we will use the other one to track back through our decisions to figure out that this is actually item 1 and item 2. Obviously, if you have 4 items, you can eyeball it. You can figure out right away, oh, okay, it's these guys. These 2 guys add to 7. But if you have, like, you know, a huge table of hundreds of columns and rows, and you have hundreds of items, so obviously eyeballing it is going to be a tedious task, and you might make some error. So it is better to use another array that just tracks where did we change the items. And again, you will see this in the tutorials. And you will walk back from the bottom cell, bottom right cell. You will walk upward until you find all the changes that you have made before, since from the minute you started solving in the first row, and that will tell you which items actually will sum up to 7. Okay? So this is what I have been referring to. You see in the top 2D array the values we have been working with the final finding that the optimal solution is 7. What you see at the bottom is an array that we're also going to maintain and update as we generate solutions in the top 2D array. In the bottom array, we are going to use the cells to track where did we actually get the value from. This will enable us, after we are done finding our optimal solution, to track back through this array of trues and falses or ones and zeros to find out what are actually the items that we have to include in the back. I haven't cared to actually fill in the bottom array. You will see it getting filled in the tutorials, but I'm just showing you that we're going to have another 2D array of flags. And just to get an idea how we're going to fill this, if you look at the bottom right of this array at the bottom, you see the 7 is marked with a true. This is our final optimal solution, and I got that from the cell above it. So when I'm actually putting the 7 highlighted in red, and I'm updating the last cell in the bottom array, I will update the flag in the top cell, which is highlighted in green, and this is actually where I got the 7 from, so I will set that to true. And along the way also, when I inserted the 7 that's highlighted in green, I also will update the cell above it, because this is where I got that 7 from, which is underlined. So basically, as we fill in the cells, I'm gonna indicate in the flags where is this value coming from, so I can later on reconstruct my solution. Now, this is just one way to do it. There are other ways. I will show you in the next slide another way how you can actually track back through your solution to find out the items you're supposed to pick. Here is the other variation, and in this variation, instead of using a second 2D array of Boolean values, I will convert the cell in the array I am generating the solutions in to be a 2D array of objects instead of being a 2D array of integers. And each object now will hold the value that is being calculated, or the number 7 or the number 5 or the number 4, as well as pointers to which items will actually give us this value. So for example, 7, as it's highlighted in red here, I will get 7 by including item 1 and item 2 in the bag. So I will have references. So I basically have references pointing to item 1 and item 2. So you could think of this like this, inside each one of those cells in the array, there is a linked list of references. And this linked list of references are pointing to objects that I can put in the bag. Okay, so the items will be maybe an array of objects or an array of items, and I will have the linked list of references inside each cell pointing to the appropriate item to get the value I have generated as an optimal solution for the specific case I'm solving then. There are pros and cons for each approach. What this approach saves you is maintaining another 2D array of true and false values. Now, this approach will consume more memory if you're working with a huge number of items. So if it's the case and you have a huge number of configurations or levels in every dimension, then you resort back to an array of booleans, which you've seen in the previous slide. It's going to be more memory efficient. Now let's move on to something else. We've already discussed graphs extensively. I've given you an introduction to graphs. You have seen it also, I know, in the course Theory of Computation. So let me show you one graph algorithm that uses dynamic programming as an example of applying the ideas we have been discussing about dynamic programming, which is the optimality property and this notion of the structure that you have somehow to devise or identify to be able to reach to an optimal solution from smaller optimal solutions, and this notion of also that some of the problems appear over and over again. So the specific graph problem we're going to look at is what's called the shortest path problem. You're given a graph, it could have hundreds of nodes or vertices, and you would like to find the shortest path between a starting vertex and an ending vertex. There could be many ways that will take you, for example, from A to C, but you want to pick the set of edges that will take you from A to C with the smallest sum of edge weights. Usually edge weights would reflect a cost that you have to pay to traverse from one vertex to another. That cost could be actually the distance in kilometers if this graph is a one-to-one representation or mapping between an actual geographic map and a graph. So it could be basically the set of roads in a city, and you would like to go from a starting point to an ending destination using the shortest path. Okay, so this is the problem we're trying to solve. So let's think of the properties, the optimal substructure. Okay, now DP thinking goes like this. I can't solve the initial problem, it's too complex, so I will try to solve a smaller version, but then I will find that the smaller version is also complex, so I will try to reduce it further to an even smaller version. And I will keep reducing all the way till I am working with an extremely trivial problem that I know I could solve right away without a lot of thinking. It's just the answer is almost intuitive, and I can code it quite simply by a number of a small number of coding statements. So instead of actually thinking about finding the shortest distance between A and C, I will try to reduce this problem. Okay, this is the substructure. This is what we refer to as the substructure. We're trying to simplify the problem. So instead of doing A to C, where I could have like hundreds and hundreds of vertices and edges between A and C, I'm not going to solve this one. Okay? So what I'm going to do is I'm going to solve something else. What is the something else I'm going to solve? I will assume that since since this graph is not trivial, there's no edge connecting basically A to C. I mean A to C directly. There will be many vertices and edges between A to C. So instead of solving the initial problem, which is find the shortest path between A and C, I will try to find the shortest path between B and C, where B lies in the middle between A and C. And if I can find, an optimal solution to take me from, say, C to B, then I've jumped, say, half the way to A. And consequently, I can find the optimal solution to A. But we're going to apply this idea recursively, or many, many times, not just one time. Okay? As for the second property, which is the overlapping subproblems, they do exist in any graph. If you just look at this graph with the start node vertex being A and the end being J, I've highlighted with the pencil tool in PowerPoint just 4 of the paths that are possible. So you have the path that is in blue, another one in red, which goes A, B, E, F, G, I, J, and the one in yellow which goes A, B, F, I, J, okay, and the one in purple which goes A, C, F, H, J. So all of these are passes that will take you from the start node to the end node. And when you're actually trying to evaluate the cost of each one of those passes, you will evaluate a portion of the graph that you will also evaluate when you try to consider other passes. So in terms of the existence of subproblems in a graph, that's guaranteed to exist unless you're dealing with a special kind of a graph where there's only one path from every node to another node. But the general case is, as you will see, if you try any number of passes, you will see that there is an overlap between them. Any number of passes, I mean between a starting vertex and an ending vertex, there will be an overlap. And that's the overlap that we are referring to as overlapping subproblems, because if you solve it once, then you're going to go through the same path again, then don't solve it again, just use the solutions you have developed before. And this is the idea of overlapping subproblems. So generally, they do exist in graphs. Now, so let's look at this graph. I would like to go from A to J. Obviously, there are many ways we can go from A. So what we're going to do is we are going to use a function to track the cost, the optimal cost that we will have to pay, or the distance we have to travel to reach to our destination. But remember, the way this works is we will assume that when we are standing at any node that it is our destination. But we will keep track that our final destination is J, and we will use that information at the end. But for now, we will use this f of J to say this is the cost we're going to pay if we would like to go to J. And since we are starting from the destination, the cost to go to J is 0 because we're already there. Now, once we have found the cost to go to a specific node, we move backward one level away or 1 degree away from one step away from the node. So f of J is 0. We have found that. F of H is 3. Which means if I'm standing at H, I will have to travel 3 kilometers to go to J. F of I is 4. So if I'm standing at I will have to travel 4 kilometers to reach to J. So this function is in relative to always J. Now, we will expand further, as I mentioned already. Now, F of E means how much I'm going to travel from E to reach to J. Now, from E, I have two edges. One whose cost is 1, that will take me to h, and another one whose cost is 4 that will take me to I. And from there, I have edges that will take me to j. So the question is, which one should I follow? Or which path should I follow from E to J? Should it be E, I, J, or E, H, J? So what I'm going to do is I will calculate the cost of going through both passes, E, H, J, E, I, J, to figure out the one that has smaller cost. So to go to H, then I will pay 1 plus H will cost me 3, so that's a 4. To go to I will pay 4 and I will cost me 4 to J, so the total cost is 8. And this is why the formula says up there, f of E is the minimum of the possible choices in front of me, the possible edges I could follow. If I follow one, if I traveled 1 kilometer, which is really nice, it's a small distance, but then I will have to pay 3 kilometers later on because H to J, I have to travel 3 kilometers or basically pay 3. The same thing, if I travel 4 to I, then I have to pay another 4 to go to J. So it's the minimum of both passes, and the minimum is 4. So f of E is 4. Okay? This is how we will proceed, because there could be several edges coming out from the same vertex, and the question is which one is shortest, but not just the shortest distance taking us from this specific node we are at to the next node, but the shortest overall distance. And this is why this will be an optimal solution. Okay? Because if there was a better path, I should be picking it along the way. Now I'm going to do the same for f. So f of f is going to be computed like this. I have two edges coming out from f. F to h, that's a 6, plus the 3, that's a 9 to reach to j from f. And then f to I, that's a 3 plus a 4, so that's a 7. So if I go to h and then j, f h j is 9, f I j is 7, so f of f is 7, and that is the most optimal cost I have found. Now I will go to G and do the same exercise. G has two edges, one going to H, that will cost me a 3 plus another 3, so that's a 6, or it will go to I, that's a 3 plus a 4, that's a 7, so f of G is 6. Okay, the minimum of both paths costs. Now I will move one level away from these nodes to the level before it. I will calculate f of b. F of b is interesting. It has three edges coming out, 7, 4, and 6. So 7 plus f of e, or 4 plus f of f, or 6 plus f of g. Okay? And f of e, we said, is going to be 4, and it's going to be the minimum. I will add to it 7 to travel from b to e, so the minimum is 11. The other one is going to be 4 plus f of f. F of f is 7 as well, so it's going to also be 11. The third one is going to be 6 plus f of g, so that's a 6 plus 6, that's a 12. So my minimum is 11. Okay? Now we move on backwards, so f of b is 11. Oh, sorry, we still have to do f of c. F of c is going to be 3 plus f of e, or 2 plus f of f, or 4 plus f of g, and the minimum is 7 again. Okay? Where did we get the 7 from? Can you figure it out? It's going to be c plus f of e. F of e is 1 plus 3, 4. F of e is 4, and c to e is 3, so it's going to be 3 plus 4, 7, so that's the smallest distance we can travel from C to the destination. Then we do the D. D is going to be 4 plus f of e, or the minimum of 4 plus f of e, 1 plus f of f, and 5 plus f of g. So the minimum here is going to be 8. 4 plus f of e is going to be 4 plus 4. That's the 8. 1 plus f of f is going to be 8 as well. 5 plus f of g is going to be 11, so the minimum is 8. We go back one level away, or one step away, and we will calculate f of a. Now f of a is going to be 2 plus f of b, or 4 plus f of c, or 3 plus f of d, and we got to figure out the minimum, and this will be the path we travel. So it's going to be 2 plus f of b is 11, that's a 13, and then 4 plus f of c is a 7, so that's an 11, and then 3 plus f of d, that's a 3 plus an 8, that's an 11. Okay, so we're going to pick the 11. Now, as you notice, there are multiple answers. There are 2 11s here, and before we've seen 2 7s. That's okay. You know, the point is you're going to pick one of them to be in your path. Okay. Now, we've actually reached to our destination, and the shortest path is going to be 11, according to our computations here. And this is going to be the path that we are referring to. Okay, A to D to F to I to J, and that would be the shortest path between those 2 vertices. The nice thing about our algorithm here is that just like many DP algorithms for graphs, it's implemented using a 1D array, where you declare an array of integers or of objects, as I've described before, to be able to track where is your answer coming from, and then you just have a for loop that goes from the beginning of the array to the end of the array, filling in the array with solutions. Obviously here there will be some kind of graph manipulation, so you need to be able to position yourself at the destination and then ask a question about who is connected to you. But we will talk about how you represent graphs later on, and that's not a big deal. So the actual code to find the shortest path here is going to be very small, probably less than a page length. And final solution is in the last cell when you reach your starting vertex. Now, there is also something I would like to note about this algorithm, which I hope you already kind of figured it out, is that it is not just finding me the shortest path between the starting vertex A and the end vertex J. It is finding me the shortest path between any vertex in J. For example, if I'm standing at B and I would like to go to J, f of B is the smallest distance I can travel. It's the smallest cost, because f of b is optimal solution. So this algorithm is actually not just finding me the shortest distance between 2 vertices, it is finding me the shortest distance between any vertex and my destination. So f of c is optimal. If you notice, f of c is 7. If you actually decide to start from 7 and you ask the question, what is the shortest path between c and j, we've actually found it along the way. Okay, f of c is 7. Okay, you're going to follow the C to E to H to J. Okay. Similarly, if you start at D and you ask, what's the shortest distance between D and J? F of D is 8, and that's the shortest distance then that you could ever travel, which is D to E to H to J. Other options are going to be more expensive, and this applies to all the vertices. Okay, so we have found all the shortest passes between all vertices A and J. Now, finding out the actual path, like what you have here in the last cell is the number 11, and that's the shortest distance between A and J. But what is the path? We will go back to the same issue we discussed earlier, which is that in DP, usually the algorithm, you find the optimal solution in, or you store the optimal solutions in, will not reveal to you right away the actual solution. They're just giving you the optimal value, which is 11 in this case. So you would need to maintain either a separate array where you track where are you going or where have you been, or you turn the cell in the array to an object and you store references. So in this case, f of a, where it says 11, it's not going to be just a number 11. This is not going to be anymore an array of integers. It's going to be an array of objects, and inside that object I will find the number 11 as an attribute, and I will also find an accumulation of the edges I'm supposed to follow. It's going to be the A, D, F, I, J. There will be references to these edges and vertices. Okay. So that's something we always have to do, and it's an additional work that is usually not expensive at all. Now, to convince you that dynamic programming algorithms or solutions will always give you optimal results compared to at least greedy, let's work out a greedy version of an algorithm that tries to find the shortest path. And this is really naive. There is really nothing intelligent about it. We're just going to be greedy if we would like to minimize the total sum of the edges between two vertices. Let's always pick the smallest whenever we face a choice. So I'm starting from A, and I see these three edges. One takes me to B, another one takes me to C, and a third one takes me to D. I will pick the edge that takes me to B because its cost is less. So I go to B, and now I will have to travel those 2 kilometers. Now when I'm at B, again I will do a naive approach in picking. I'll say, okay, I got an edge taking me to E and it's 7, and an edge to F and it's 4, and an edge to G and it's 6. Let's pick the minimum, and the minimum is 4. I'll do the same thing at the F. I will pick the edge that takes me to the I because the minimum is 3. Between 3 and 6, the minimum is 3. And then when I'm the I, I'm forced to go and follow this edge to the J. Now my total is 13. As you see, a greedy approach would not necessarily result in an optimal solution. We have found it that it is actually using DP, it is actually 11, because the DP way of thinking is generally thought of to be smarter than greedy. While greedy, you just look at the choices in front of you and you don't look ahead. The way the DP works is that we're always picking an optimal solution by considering all the options up to now, while this doesn't show up actually at all here. So in conclusion of today's lecture, these are the references and the textbook to download, and the specific pages in the Goodrich and Tamassia textbook for reading about the 1.0 knapsack, and an intro to DP. I have included both textbooks, Goodrich and Tamassia and Corman. Start as always by the Goodrich because it's simpler to read, and then move on to the Corman and do the reading there.